The next topic is going to be properties of electric field lines or lines of force. So based on the previous topic that we discussed, that is how to draw the field lines for each charge, let's try to frame the properties that electric field lines follow. So the first point that we are going to see is they start from the positive charge. They start from the positive charge and end with the end at the negative charge. Remember, this is the most important point. Like for example, when you look at this diagram, the diagram number 3, they start at the positive charge and they terminate with the negative charge. They do not form a closed loop. So in your 10th standard, you would have learned the properties of magnetic field lines. It is something similar, but the only difference is going to be magnetic field lines form a closed loop, whereas electric field lines will never form a closed loop. It is a very important point to be noted. That is, they never form a closed loop. The second point. So lines of force do not intersect. The electric field lines or the lines of force do not intersect. So this is a mostly asked one mark question. So they say electric field lines do not intersect. Let's see what is the reason for it. So as we discussed in the previous topic, observe, I told you if you need to find the direction of electric field at a particular point, you need to draw the tangent at that particular point. Okay. So the tangent at a particular point will tell you the direction of the electric field. But what is the significance of electric field, the direction of electric field? It is going to be the direction in which a unit positive test charge would start moving if it is free to do so. So if the unit positive test charge has the freedom to move, in whichever direction it is going to move will give you the direction of electric field at that particular point. So that's what we discussed. If suppose with respect to this diagram, if I place it here, then I'll draw a tangent in this way. This is the direction in which Q0 is going to move, right? If suppose they intersect, let's see what is going to happen. Say if suppose I draw two field lines like this. I say this is one electric field line and there is another field line. If suppose they intersect, if I place a charge Q0 here, then how many tangents are possible at this place? So there are two tangents that you can draw. So here, what do these two tangents signify? They are trying to tell us that if you place a unit positive test charge at the point of intersection of these two curves, the test charge would start moving in both the directions simultaneously, which is going to be absurd, which is not possible, right? Because it is not possible for a same particle to travel in two different directions at the same instant, right? So what we are supposed to say is, the reason for this is, at the point of intersection, how many tangents can be drawn? Two tangents can be drawn. And what do they represent? That shows the test charge can move in two different directions at the same instant, which is definitely not going to be a possibility. So remember, this is a very, very important point. So this point has a link to the next chapter as well. Have this in your mind. The next point. So the next point is, we have already discussed it. So we have already discussed this point. Tangent drawn to the curve at a particular point gives the direction of electric field at that point. So this we have already seen. For example, I've already told you tangent drawn at a particular point gives you the direction of electric field. So I'm not discussing much on this. And the next point is the number of lines per unit area, the number of lines per unit area through a plane gives the magnitude of electric field intensity at that point. So what is the meaning of this? If you are able to calculate the number of field lines per unit area through a plane, that will give us the magnitude of electric field intensity. For example, if I take a positive charge, then the electric field due to a positive charge is going to be away from it. Right? This is what we had been saying. It is radially outward. If suppose I consider a small area here and I consider the same area at this point, one thing we are able to observe at location 1 and location 2, if you calculate, through location 1 there are two lines that are passing, whereas through location 2 there is only one line that is passing. So if you are able to calculate how many lines are able to pass through a given area, that will tell you about the intensity. So from this, what is that we are able to understand? More is going to be the number of field lines that are passing through a given area, more is going to be the electric field intensity. So from this we can consider electric field intensity is directly proportional to the number of field lines. Through what? Number of field lines through a given area. So this will give you the magnitude. So these are the important points about the properties of electric field lines. I would like to make a small note. So make a small note. If you are able to calculate the number of field lines through an area, and most importantly through an area, they should pass perpendicular to it. If you are able to calculate the number of field lines through an area perpendicular to it, then the quantity, the physical quantity, is termed as electric flux. So remember this term electric flux. As of now, I've just given you the definition. We'll discuss about this in depth in the upcoming videos. So I'm repeating it. If you're able to calculate the number of field lines through an area perpendicular to it, then that quantity is termed as electric flux.